Welcome back, everyone, to another deep dive. This time, we're going to be exploring something that sounds like it's straight out of science fiction.
Oh, yeah.
Yeah, so get this. We're diving into primordial black holes,
Okay.
but specifically
Right.
the ones that might be as small as asteroids.
Really?
Yeah. So you're probably thinking, black holes, I thought those were massive things that just like swallow up entire stars.
Yeah, that's what I thought. That's what we normally hear about.
Exactly. But these primordial ones, well, they might be surprisingly tiny.
Wow.
And it gets even weirder when we start thinking about the physics of them at that scale.
I bet. That sounds pretty wild.
It is.
So we're talking about the wild world of quantum mechanics when we get that small, right?
Yeah, exactly.
And, you actually sent me a research paper to dig into all this. It's called Quantum Mechanical Suppression of Accretion by Primordial Black Holes.
I am very intrigued by that title already.
It's by Abraham Loeb from Harvard University, and it really dives into how, these smaller black holes might not be the ravenous cosmic vacuum cleaners that we imagine.
Yeah, that's what I think of, yeah.
Yeah.
Huge, like sucking things in.
Yeah, just gobbling everything up.
Yeah. So, okay,
Yeah.
just for context, most black holes, the ones we normally hear about, those are formed when huge stars collapse, right?
That's right. Yeah. Big stars collapsing in on themselves.
But these primordial ones, they're different.
Yeah, they are different. We think these might have actually formed right after the Big Bang.
Oh, wow.
So very early on in the universe. And they could range in size from smaller than an atom
Wait, what?
to, well, asteroid size.
Hold up. Smaller than an atom. My brain is already struggling with that visual.
Yeah, it's pretty mind-bending, right?
Yeah.
Basically, a black hole size is related to its mass.
Okay.
And there's this thing called the Schwarzschild radius, which is kind of like the point of no return. Anything crosses that boundary, it's trapped. And the paper calculated that a black hole with the mass of, say, like a decent-sized asteroid could have a Schwarzschild radius the size of a hydrogen atom.
So we're talking about packing an incredible amount of mass into an unbelievably tiny space.
Yeah, it's hard to even picture.
It is. But then how do they even eat anything at that scale?
Right.
Wouldn't the laws of physics just get in the way?
That's exactly what this research is all about.
Okay.
You'd think, okay, primordial black holes, they're just constantly gobbling up matter, right?
Yeah.
But quantum mechanics throws a wrench into things.
Okay, I am all ears. How does quantum stuff affect a black hole's lunch plans?
Okay, so imagine trying to cram a whole watermelon into a thimble.
Okay, that's not going to work.
No.
No.
At the atomic level, these tiny black holes face a similar problem. Instead of just a smooth inflow of matter, they're forced to interact with individual atoms or even smaller particles like protons and electrons.
Oh, wow.
One at a time.
So it's less of a cosmic vacuum cleaner and more like, I don't know, cosmic tweezers carefully picking up individual particles.
Yeah. That's a great analogy. And it gets even more complicated because, electrons are fuzzy, spread out things according to quantum mechanics.
Right.
So even if a black hole grabs a proton, the electron might actually end up outside the event horizon.
Wait, so the black hole could end up with an electric charge?
Yeah, exactly.
Oh, wow. So then what happens? Does it start repelling other particles?
That is one of the fascinating scenarios that's explored in this paper.
Wow.
If a black hole becomes, say, positively charged by capturing a proton, but not its electron, well, that charge is going to affect how it interacts with other particles.
Right, of course.
It's like adding another layer of complexity to the already mind-boggling physics happening at the edge of a black hole.
My mind is officially blown. So we've got this tiny black hole, smaller than an atom, maybe even with an electric charge, and it's trying to eat in a universe governed by quantum mechanics.
Right.
What does that actually mean for how these things grow over time? Could they even get bigger?
That's the million-dollar question.
Yeah.
And that's where things get really interesting. We'll need to delve into something called the accretion rate, which basically tells us how fast these black holes can actually consume matter.
All right, lead the way. I am ready to dive into the next level of this cosmic mystery.
Okay, let's do it.
Okay. So we're back, and I think we're ready to tackle this idea of the accretion rate.
Yeah, let's do it.
The paper mentions it a lot, and I have to say, I usually like a good physics formula.
Okay.
But I need a little help translating this into something I can wrap my head around.
Totally understandable.
Yeah.
So to understand how these tiny black holes might grow, we need to kind of compare what we're learning about them now
Okay.
to what we used to think.
Yeah, okay.
So traditionally, astronomers have used this thing called the Bondi accretion rate to estimate how much stuff a black hole can pull in. And it's based on this idea of a black hole just kind of sitting there in a smooth, fluid-like medium, swallowing anything that gets too close.
Right, kind of like that classic cosmic vacuum cleaner idea we talked about.
Exactly.
But we know that that doesn't really work for these primordial black holes, especially when they're dealing with individual atoms.
Yeah, it's a different ball game down there.
Right.
So what Loeb's research highlights is that the actual accretion rate for these smaller black holes can be much, much slower than what the Bondi rate would suggest.
Really?
Yeah. And it's all thanks to the weirdness of quantum mechanics at these scales.
Okay. So if the Bondi rate is like the theoretical speed limit, these primordial black holes are stuck in the slow lane.
Pretty much, yeah. Imagine you have a primordial black hole with a mass similar to, let's say, like a small mountain range, right?
Okay, yeah. I can picture that.
And it's hanging out in cold, sparse gas where electrons are all bound to atoms. Well, the paper estimates it would take longer than the entire age of the universe for it to grow significantly.
Wow, talk about a cosmic diet.
Right.
So even if these primordial black holes were super abundant in the early universe, they wouldn't have grown much at all.
Not necessarily. So while they might struggle to gain weight in those sparse areas, things change dramatically when they encounter denser environments.
Okay, so where would those be?
Think about, like, the interior of a star or even a planet.
Ah, so they could still pack on the pounds if they find the right cosmic buffet.
You got it.
Okay, that makes sense.
The research points out that in those denser environments, atoms are packed so tightly that they actually get closer together than the black hole's gravity can distort them.
Oh.
So that means the black hole can potentially capture multiple particles at once, and that really gives its growth a boost.
Okay. So while quantum mechanics might slow them down in the cosmic suburbs, they can still make up for it in the bustling city centers of the universe.
That's a great way to put it. Yeah, and in fact, the paper even explores a scenario where a primordial black hole gets trapped inside a white dwarf.
Oh, wow.
Which is incredibly dense. And in that case, the Bondi rate suggests the black hole could grow rapidly, maybe even causing the white dwarf to collapse.
Oh, so they're like hidden time bombs.
It's a fascinating possibility.
That is fascinating, yeah.
But we do have to remember there are other factors at play here, too.
Okay, like what?
Well, the paper mentions the Eddington limit, which is like a natural cap on the accretion rate. It's caused by the outward pressure from the black hole's own radiation.
So it's like a cosmic tug of war. Right. Gravity pulls stuff in, radiation pushes it back out.
Exactly. And to make things even more complex, we have to factor in Hawking radiation, which causes black holes, especially smaller ones, to slowly evaporate over time.
Okay, yeah. Hawking radiation, that's that quantum effect where black holes can actually shrink and eventually just disappear.
That's the one.
Does that mean that even if they find a dense environment to grow, they could still be fighting a losing battle?
Absolutely. So for the smallest primordial black holes, Hawking radiation could easily outpace any growth from accretion, leading to their eventual demise.
So it's like a cosmic balancing act then.
Yeah.
We've got quantum mechanics, we've got gravity, and we've got radiation all playing a role in the fate of these tiny black holes.
It's a complex interplay of forces.
It is. But even with all of that, why should we even care about these things?
Yikes.
I mean, are they really that important in the grand scheme of the universe?
For one thing, they might actually be a big part of the mystery surrounding dark matter.
Oh, here we go. I knew dark matter had to enter the conversation at some point.
Had to.
Yeah. But how could these tiny black holes possibly account for something as massive and as widespread as dark matter?
Well, it comes down to their potential abundance.
Okay.
The idea is that if enough of these primordial black holes formed in the early universe and managed to survive all the factors we've been discussing, they could collectively contribute a lot of that missing mass that we observe.
So even though these black holes might be picky eaters and face all these challenges to grow, they could still be subtly shaping the structure and evolution of the universe.
That's the exciting part. And studying them might give us a unique window into the physics of the very early universe.
Wow.
Maybe even helping us solve the puzzle of dark matter and quantum gravity.
Okay, now that's what I'm talking about. Probing the fundamental mysteries of the universe using black holes that are smaller than atoms.
It's pretty mind-blowing stuff.
It is mind-blowing. Okay, so we've covered the strange way these black holes feed, what limits their growth, and this potential connection to dark matter.
We've covered a lot of ground.
We have. But, call me a worrywart, but what does all of this mean for us here on Earth?
Okay.
Could these primordial black holes pose any danger to our planet or solar system?
Well, that's a question many scientists have explored, and the good news is it seems very unlikely.
Okay, that's reassuring. But why are scientists so confident that we're safe from these tiny black holes?
Yeah.
I mean, they're still black holes.
That's true. But remember, even though we're talking about asteroid-mass black holes, they're incredibly small, sometimes even smaller than an atom. So even if one were to pass through our solar system, the chance of it interacting with anything is incredibly low.
So it's a matter of scale.
Yeah.
They're just too tiny to cause any significant damage.
Exactly. Think about it this way.
Okay.
Earth is constantly bombarded by cosmic rays, right?
Right.
Which are these high-energy particles from space.
Mm-hmm.
These particles are much more likely to interact with matter than a primordial black hole would be.
Okay, I'm starting to feel a bit better about this whole thing.
Yeah.
But what if one of these black holes did actually collide with a planet or a star?
Okay.
Would we even notice?
Yeah, that's a good question. It's true that a direct hit from a primordial black hole, even a small one, could have some effects. But the vastness of space makes those encounters incredibly rare.
Okay, so we can rest easy knowing that these primordial black holes, despite their bizarre qualities, aren't likely to cause any cosmic chaos in our neighborhood.
That seems to be the consensus, yeah. But that doesn't mean we shouldn't be fascinated by them and keep exploring their mysteries.
I totally agree. This has been an amazing deep dive into the world of primordial black holes. Is there anything else from the paper that stands out to you before we wrap things up?
Well, the paper really emphasizes that this quantum mechanical suppression of accretion is really key to understanding how these primordial black holes, especially those in the asteroid mass range, behave and evolve. And it even suggests that if we could actually observe one of these things directly, it could be a testing ground for theories about quantum gravity.
Oh, wow. A testing ground for quantum gravity. That's incredible. Okay, well, we'll have to leave it there for now, but this has definitely sparked my curiosity about these really enigmatic objects. It feels like we've only just begun to scratch the surface.
Yeah. It really is amazing to think that something so tiny could potentially hold the key to such huge mysteries in the universe.
Yeah, it really speaks to how interconnected things are in physics.
Right.
From the smallest quantum scales to the largest cosmic structures, it's all intertwined,
Absolutely. And speaking of interconnectedness, there's one final idea from the paper that I just have to unpack a little bit.
Okay.
It mentions the possibility that these primordial black holes could be hiding inside planets or stars.
Yeah.
Even subtly influencing their evolution.
That's one of the most intriguing implications of this whole concept.
Right.
It paints a picture of these tiny giants lurking within celestial objects, almost like a cosmic game of hide and seek. But how would that even work? Could a black hole, even a small one, survive inside a planet or a star without completely tearing it apart?
Well, it's a matter of balance. Remember, these primordial black holes are incredibly small.
Yeah.
Their gravitational pull, while intense at close range, falls off very quickly as you move further away.
So it's kind of like having a tiny, dense pebble embedded in a giant ball of dough.
Yeah.
It might create a little dimple, but it wouldn't necessarily destroy the entire thing.
Exactly. The paper suggests that a primordial black hole could potentially orbit within a planet or a star, slowly accreting matter and releasing energy as it interacts with its surroundings.
So that's a pretty wild concept.
It is.
So could we actually detect these hidden black holes? Would there be any observable effects?
Well, that's where things get a little tricky. The effects would depend on a lot of factors. The black hole's mass, where it is within the host object, the composition of the material around it, and so on.
So no easy answers, then?
Not really, but scientists have come up with some interesting possibilities.
Whoa, wait, what?
For example, a black hole hiding inside a star could subtly alter its brightness.
Okay.
Or how it pulsates.
Uh-huh.
It could even affect the star's rotation, maybe leading to some unusual activity on the surface.
Oh, wow.
So we could potentially detect these hidden black holes indirectly by looking for anomalies in the behavior of stars and planets.
It's almost like a cosmic detective story.
Precisely. And as our telescopes and observational techniques get better, we might be able to pick up on the subtle fingerprints of these tiny giants hiding within larger celestial objects.
That's so cool.
It is pretty neat.
This whole deep dive has really shifted my perspective.
Yeah.
I'm seeing these primordial black holes not just as like theoretical oddities, but as potential actors on a cosmic stage, maybe even shaping the universe in ways we're only beginning to grasp.
It's exciting, isn't it?
It is. And I want to thank you for guiding us through this fascinating exploration of primordial black holes.
It's been my pleasure.
And to you, our listener, we hope this deep dive has sparked your curiosity about these enigmatic objects.
Yeah, keep exploring.
And inspired you to continue your own journey of discovery.
Absolutely.
Until next time, happy diving.